Hi, I'm Pierre Deymier. I'm the director of the New Frontiers of Sound Science and Technology Center at the University of Arizona. I'm going to show you what we're doing in the University of Arizona laboratories of the center. We're working on materials for radio frequency devices. These are devices that appear in your cell phone and that make your cell phone function. The traditional material for this is lithium niobate, which is a piezoelectric material. However, these material properties are difficult to modify. So in this laboratory, what we're doing is we're combining piezoelectric materials like lithium niobate with materials that are used in compact disc writable and rewritable technologies in such a way that we can modify and tailor the properties of the lithium niobate, including the phase change material, so we can make radio frequency devices which are reconfigurable, which do not exist at this moment. Let me take you further into the laboratory. These phase change materials are effectively composed of germanium, arsenic, tellurium, arsenic being toxic. We do most of the work in this glove box. However, some of these materials are laser writable, just like your old CD-ROMs. So in this laboratory, we use lasers to pattern the phase change materials that is combined with the lithium niobate to achieve reconfigurable properties. Of course, in a materials science and engineering laboratory, we need to do materials characterization, which is done in this laboratory, where we investigate the properties of the phase change materials when we heat the material, like with a laser. We can change the state of the material from a glassy state, like window glass, to a crystalline state, like a quartz crystal. But we also analyze the properties of these materials using spectroscopy. So the New Frontiers of Sound Science and Technology Center is transdisciplinary. You saw the materials fabrication lab, which enables us to fabricate radio frequency devices which are going to be reconfigurable. But let me take you also in the acoustic lab, where we do characterization of these devices. So if you follow me, these radio frequency devices operate at telecommunication frequencies. In our case, we're operating at 200 megahertz. And those devices that include the lithium niobate and phase change materials are put in these probe stations, which enables us to look at their electrical properties and therefore the properties that they will exhibit as devices inside your cell phone. And we're trying to design such devices which reduce the amount of power that you need in your cell phone for telecommunication. In this acoustic lab, we are also working on a project which involves acoustics as an analog to quantum information science. So follow me here and I'll show you a system that is analogous to a quantum computer, but which is much simpler. What we do is we work with materials that are essentially waveguides which are coupled with each other. These are acoustic waveguides. These acoustic waveguides are mounted in such a way that they can be excited on one side with piezoelectric transducer, very similar type of materials that I talked about earlier in radio frequency devices. We drive the system with this amplifier and signal generator and create waves that are superposed in this system. And these waves then are shown to be analogous to the famous quantum bits or qubit bits, which enables us to perform operations and computation using this very simple acoustic analog quantum computer. Quantum information science is a very promising technology which will enable quantum computers to do fantastic amount of data processing. However, they suffer from some technological challenges, such as the instability of quantum information, and require tremendous equipment, especially cryogenic temperatures, to operate. Our system here does not need cryogenic temperature. It can operate at room temperature, giving it an advantage over existing quantum technologies. To analyze the properties of this system, we also perform measurements using a laser Doppler vibrometer, which enables us, by shining a laser onto the waveguides, to record the motion of the waves within this waveguide and analyze their properties such that we can predict their behavior for operating our quantum analog computer. But this laser Doppler technology is not just limited to being used for our quantum analog computer. We also use it to do sensing. When in the aerospace industry, people fabricate parts like a jet engine or part for a jet engine, it is critical that these parts do not include any flaws, such as crack, for instance. If you have flaws, then the part may crack, and eventually your airplane may crash. So let me take you into our non-destructive evaluation testing laboratory, which involves a laser Doppler vibrometer, similar to the one that you saw before, but which can operate at the micro scale. Here what we do is we consider parts that have been manufactured with additive manufacturing, and by using the laser from this system and vibrating the part, we are monitoring the state of vibration or the acoustic waves that are supported by this part, and we analyze this data to identify the presence of flaws like cracks in this material. This enables us to really separate the parts that have defects from the parts that do not have defects. This technology here has a very strong potential in improving the quality of parts that are used in aerospace applications.